Now, now let's move on to the next part of the Bohr Einstein debate. And now we are reaching out where we have a conference, the Bohr Einstein Debate. And the conference that we have, we call it Solvay Conference, where you have these giants, and these giants challenge it reality. So, ladies and gentlemen, we have now reached one of the most fascinating chapter in the history of science. Everything we have discussed so far, the discovery of quanta, Einstein's explanation of the so-called photoelectric effect, and then we have Bohr atomic model, and we also talked about the wave-particle duality, and of course the emergence of quantum mechanics. And it was all basically preparing. We were trying to prepare the stage for an extraordinary intellectual confrontation. The confrontation that did not take place in a courtroom. It's not that kind of confrontation that we have been talking about. It did not take place in any kind of parliament. It took place in a scientific conference hall. Yet the questions debated there, they were among the deepest humanity has ever asked in the field of science. So those meetings became famous as the Solvay conferences. Beginning in 1911, the Solvay conference brought together the greatest physicists in the world of that time. Imagine entering a room containing many of the scientists who had built modern physics. The atmosphere was not one of competition for fame. It was a shared search for truth. Everybody looking for the truth. Now, yet within that room, two very different visions of nature gradually emerged. On one side stood the Neil Bohr, and Bohr believed in quantum mechanics, although strange. It was strange fundamentally, but fundamentally it was correct. Now, according to him, the microscopic world cannot always be described using the language of everyday experience. What we experience in everyday is classical mechanics. So classical ideas like definite position, definite momentum, and continuous trajectories, all of these things have limited applicability at the atomic scale. Now, on the other side, what we have the genius, Albert Einstein. And Einstein deeply admired the mathematical power of quantum mechanics. Pure. And he repeatedly acknowledged that quantum mechanics produced remarkably accurate predictions. However, he was convinced that it did not tell the whole story. It's very important, basically. It's something very important to understand the Einstein's position correctly. Einstein was not basically arguing. He was not arguing that the experiments were wrong, the predictions of the experiments were wrong. He was not arguing that quantum mechanics should be discarded. His argument was more subtle. What he believed that quantum mechanics was an incomplete description of reality. In other words, he thought there must exist some deeper theory beneath quantum mechanical framework. He believed that there could be a theory that would restore the so-called causality and provide a complete description of nature of reality, a complete description of physical world. Now, this distinction is often misunderstood. Einstein respected quantum mechanics and he respected this framework enormously. His dissatisfaction was philosophical, and at the same time, it was scientific. It was not emotional. Now let's understand the heart of the disagreement between Niels Bohr and Albert Einstein. Now, first, imagine tossing a coin. Okay, we toss a coin. Now, before you look, you might say there is 50% chance of getting head and 50% chance of getting tail. But everyone agrees that the coin has already landed one way or the other. Your uncertainty exists because you lack information here. So lack of information leads to that uncertainty. And nature itself is not uncertain. This is what's called as classical probability, tossing a coin. And Einstein believed quantum mechanics. I mean, he believed in quantum probabilities. These quantum probabilities should be understood in a similar way. This was the argument. And he suspected that there were some hidden details, unknown variables that determine every outcome. So quantum mechanics appeared probabilistic, simply because those deeper variables had not yet been discovered. And against this argument, we have Bohr. And Bohr disagreed with this argument. He completely disagreed. Now, according to Bohr, quantum probabilities are not merely expressions of what we may call as human ignorance. According to him, they are a fundamental feature of nature itself. The theory does not hide a more detailed classical picture. It is the most complete description available. Now, this difference may sound abstract, but I should tell you that it has enormous consequences. Now, if Einstein is correct, then every event has a definite cause. Even if we don't yet know it. If Bohr is correct, then nature itself is fundamental. And nature has its own fundamentally probabilistic nature at the quantum level. Now try to notice that this debate was never about intelligence. Quite evident that both men were brilliant enough. It was about the nature of reality. Now, another towering figure is entering this ball game, is entering in the story, and his name is Werner Heisenberg. In 1927, Heisenberg formulated what became known as the uncertainty principle. And this principle is often misunderstood. I mean, it does not say that our measuring instruments are simply imperfect, nor at the same point of time does it say that scientists are careless while making this measurement between position and momentum. Now, instead, it states that certain pairs of physical quantities, most famously we know as position, momentum, energy, time, they cannot both possess arbitrarily precise values simultaneously. And that too simultaneity in the framework of quantum mechanics. The more precisely one quantity is specified, the less precisely the other physical quantity can be specified. This is not merely a technological limitation as per the Werner Heisenberg's principle. It's built into the mathematical structure of quantum mechanics. Quantum mechanics itself. The mathematics here expresses this through the so-called operators. And these operators do not commute. Without writing down the equation here, the essential idea is that the order in which certain quantum operations are performed, the order matters. That's what we can say in literal sense. And that mathematical property directly leads us to uncertainty principle. Now, when Einstein heard this, he was unconvinced. He believed that there must be a clever way. There must be some more clever way around it. And so began one of the most remarkable traditions in scientific history. So what Einstein is going to do, Einstein would spend months designing a thought experiment, indeed to expose a weakness in quantum mechanics, because Einstein is taking it as a part of weakness. He would arrive at Solvay conference and he would arrive there very confidently that he had finally found a contradiction. And guys, he would present the idea to the so genius Bohr. And Bohr would listen carefully. Then often, after an entire night of reflections, he would demonstrate why Einstein's proposed experiment did not actually violate quantum mechanics. This happened not once, but it happened repeatedly. I mean, repeatedly. The discussions often continued long into the night. Now, those who witnessed them later, they described the atmosphere as intense. The atmosphere would have been intense, but at the same time, it would have been respectful, and certainly intellectuality was there. It was electrifying. Neither scientists attacked the other's character. I mean, each attacked ideas. That's one of the finest, I believe that's one of the finest examples of how scientific disagreements should proceed. And these disagreements should move on even in social life. Now, the Einstein's most famous objection involved what is known as a photon box thought experiment. What he did, he imagined a box, okay, filled with radiation. The box contained a tiny shutter controlled by an accurate clock. Now, at a precisely chosen moment, the shutter would open briefly, allowing a single photon to escape from the box. Now, by weighing the box before and after the photon has escaped, Einstein argued that one could determine the photon's energy with extraordinary precision. Now, at the same time, the clock would determine the exact momentum of emission of the photon that's leaving the box. Now, if this were possible, what Einstein is claiming here, Einstein claimed that one could know both the energy and the emission time more accurately than quantum mechanics allowed. Now, at first glance, it appeared that the uncertainty principle had been defeated. It was seeming like that it's gone. And many people, many physicists were impressed by this idea that was given by Albert Einstein. Had Einstein finally found a fatal flaw? Bohr carefully analyzed the proposal. And then he noticed something extraordinary. The weighing process. The weighing process itself would be influenced by the gravity. And because Einstein's own theory of general theory of relativity tells us that the gravity affects not only photons, but it affects the flow of time. So the clock inside the box could not remain perfectly unaffected. You have the unavoidable gravitational effect that's induced exactly the uncertainty required by the quantum mechanics. This was the beautiful argument. It was a remarkable twist of history. Bohr used Einstein's own theory of what we know as general theory of relativity to defend quantum mechanics against Einstein's criticism. it was an extraordinary intellectual moment. And Einstein reportedly accepted that Bohr had answered his particular challenge. But he was not satisfied overall. He continued searching. He continued to go deeper into these hidden variables. He continued to go deeper and deeper in his objections. And these exchanges were not about winning the point in the debate. What basically we have is they forced the physicists to examine every assumption with an unprecedented care. Now, each challenge strengthened the conceptual foundations of quantum theory. Now, each response revealed new layers of understanding. By the end of this Solvay debate, quantum mechanics had survived. It survived every direct conceptual challenge. The conceptual challenge that was raised by Albert Einstein. Yet, Einstein remained unconvinced, looking for these hidden variables. That the story was incomplete for Einstein. He was preparing an even deeper challenge, one that would become known as EPR paradox. Now, that challenge would force all of the physicists to confront ideas that seemed even stranger than that of uncertainty principle itself. It would introduce the concept now known as